Spontaneous synchronization to speech reveals neural mechanisms facilitating language learning. Basically, matching up movements or other auditory cues to speech reveal how the brain processes learning words in language. The general experimental structure is to present a behavioral task to a population in order to separate them into two groups. When exposed to a continuous train of random syllables, some people find a match to a pattern while others will not, thus defining the two groups. With structural and neurophysiological imaging, you can see distinct differences in the two populations. The one who attempted to match with random tones and the other noises show increased stimulation to the frontal area due to precise microstructural differences in white matter pathways that connect with auditory regions. The purpose of this experiment is to attempt to understand what influences individual speech processing and language performance. The main body and what we already know. We know that from birth, humans can match body movements to auditory inputs. For example, dancing to the beat of music or swaying to a harmony. The first 3 years are crucial for brain development and therefore language development. There are critical periods where speech and language information are best absorbed. Babies learn to cry about for necessities and gradually recognize sounds to their native language and will mimic sound and body movements as observed. Most studies focus on how auditory stimulation creates motor movement, but this study attempts to convey how audio-motor system plays into speech manifestation. Furthermore, it attempts to convey when audio-motor synchronization occurs throughout life and how it affects the brain by structurally making neural connections. The experiment tests the behavioral response to spontaneous synchronization to speech. Results show a large part of the population does not show speech-to-speech synchronization. Experimenters explored how structure of the brain correlates to function without synchronicity to speech. Then, it was depicted how behavioral findings on audio-motor synchronization, such as dancing to a beat, related to a more general picture of how we process speech and learn languages. The results. Spontaneous speech synchronization reveals bimodal distribution. How results were collected. 84 participants listened to random syllable pattern at 4.5 syllables per second. After a random train or random syllables ended, the participants were asked to recall if a target syllable was presented. Target syllable being ta. Then participants were asked to recall the syllables. The synchronizations between what participants reported and the computer sounds separated them into groups. 1. High synchronizers and 2. Low synchronizers. High synchronizers more accurately remembered the computerized syllables. The groups contained no differences in language background, age, or gender. However, high synchronizers were more likely to have music background. Next, the distribution of phrase differences between what was produced and what was perceived were analyzed. High synchronizers could more accurately produce syllables and mimic a specific rhythm. The low synchronicity were, in general, unstable with phrase recognition across all rhythms applied. When syllables were produced in a non-rhythmic fashion, the high synchronizers had more difficulty recalling the syllables. Low synchronizers remained at the same competency rate. This indicates a subgroup of the population can adapt a produced rhythm to a perceived one. Most participants were consciously unaware when rate shifted, but could accurately produce the rate shift. This indicates an unconscious phenomenon in speech and language processing. High synchronizer speech output responded best to an external auditory speech rate, whereas low synchronizers showed no correlation between produced and perceived speech rhythms. It was then determined audio motor synchronicity stabilized over time, indicating synchronization as an individual trait. The PLV diagrams illustrated this was a high correlation. The R values were 0.86. After repeating the test 1 month later, the R values were 0.78. This proves the test is accurate in its ability to distinguish high synchronizers and low synchronizers. Overall, once the population was divided into high and low synchronizers based on a person's ability to correctly recall syllables, the results were consistent over time that high synchronizers could more accurately produce the perceived tone than the low synchronizers. Neural distinction between the two groups. In an experiment, participants listened to rhythmic syllables at 4.5 Hz per second, then were analyzed in an MEG machine. They had to identify a few trains of syllables to the matching tones. There was not a significance between the high synchronizers and the low synchronizers. A PLV was performed between brain activity and envelope of auditory stimuli. Results suggested speech timing during production are implicated during speech perception to track perceived syllable rate. When analyzing group differences in left Brodmann's areas 44, 45, 46, and 9 yielded no significant differences between groups. Structural distinctions showed that high synchronizers had more microstructural properties in white matter neighboring the auditory cortex. There was a lateralization pattern in white matter. Notable results were structural differences that related to auditory and frontal neurophysiological results. Increased leftward lateralization was more common amongst brain to stimulus synchronicity in left frontal regions. The results we experimenters can use going forward in discussion. The behavioral, neurophysiological, and neuroanatomical results indicate that some subgroup of the population can match speed output to speed input, while others could not pick up on a particular pattern. The behavior pattern discovered correlated with production areas such as inferior frontal gyrus and perception areas such as early auditory cortex. This has implications that word learning and cortex of speech segmentation had theoretical and practical implications for how individual differences in cognition and understanding are identified. A simple behavioral task using the SSS test, emphasizing individual differences in cognition, illuminates to changes between high synchronization and low synchronization individuals and predictive audio motor synchronization, neurophysiological function, brain anatomy, and performance on ecologically relevant word learning tasks. With this information, we can better tailor education to individuals and encourage speech and language learning in a productive manner.